Hi, my friends. We are in Algebra 2. We're dealing with Chapter 1 and we're now in the second section, Properties of Real Numbers. Our vocabulary can best be summed up with this beautiful Venn diagram that's going to talk about categories of numbers and where we put numbers and how we can deal with them. This R stands for real numbers. So all of the numbers we're going to talk about today are considered reals. So that's our real numbers. We also have in the category of real numbers, we've got the category of real numbers is broken down into two categories, Q, which are the rational numbers, and I, which are irrational numbers. Q rational, I irrational. And then we have Z, which is for integers, W, which is for whole numbers, and N, which is for natural numbers. I'm actually going to kind of start backward, and I'm going to talk about each of these in an interesting kind of backward fashion. I think it'll help you memorize what they are. And so um, when I think about the natural numbers, what I think about is being in kindergarten. And natural numbers were like kindergarten numbers: one, two, three, four. And if you remember, you didn't really talk about negative numbers in kindergarten, and you counted up as high as you could go, and that was really it. And so when I think about natural numbers, I think about kindergarten numbers starting with one and we're moving up. So counting numbers is another way that we refer to the natural numbers. Another type of number that we're going to talk about would be whole numbers. And whole numbers are not much different from natural numbers. In fact, they're just natural numbers with zero added to it. All right. So if I were to talk about the whole numbers, I'd just say 0, 1, 2, 3, and 4. And really the only difference between the two is that 0 is added to this set. Not that big a deal at all. And so with that in mind, we turn our attention to the next level of number, the integers. And integer numbers are more high school numbers, right? Sometimes I think, or maybe middle school, I think of them as the number line numbers. So when I first remember being introduced to integers, I saw them on a number line, right? And the number line not only had positive numbers, but it also had these negative whole numbers as well. So when we talk about integers, we are referring to negative and positive whole numbers. So our integers are called negative and positive whole numbers. So that's what I would refer to when I'm dealing with integers, negative and positive whole numbers. And of course, these arrows, I didn't put arrows here, but this goes on forever and ever in either direction, all right? And so now that gets us to an interesting idea. So what are rational numbers? Rational numbers are pretty cool. They are numbers. Let's use a different color to highlight these bad boys. Rational numbers, I'll use kind of a reddish color. Rational numbers are going to refer to any number that I can write as a fraction. So examples of rational numbers would be 2/7 or 10 over 5. Notice 10 over 5 really resolves to 2. So yes, it makes sense that integers or whole numbers, or even integers, whole numbers, or natural numbers, which 10 over 5 is ultimately, are also rational because they can be written as fractions. Negative 1,000 over 437. All of these are rational numbers. Rational numbers are any number that I can write as a fraction, or we would say a ratio of integers. Now, the key thing about these guys, you see we're talking about them in their fractional form. If we talk about them in their decimal form, I would say any decimal that terminates, meaning ends, or repeats in a predictable fashion. So another example of a rational number would be like 0.473, and I put a line at the top, and I know that that means 473, 473, 473 repeating after that decimal, right? So this is considered rational because I can actually rewrite this as a fraction. Even if you don't remember how to do it, we can do it. All right, and the next thing that we need to keep in mind is it can go on for a really long time. 1, 2, 3, 4, 7, 8, 9, 7, 2, 1, 1. But if it stops, totally dope, we are going to consider it a rational number. So all of these are rational numbers. Any number I can write as a fraction, or any decimal that repeats in a predictable way, or terminates. So it repeats or terminates. So that takes care of this whole category here of real numbers. Now I stands for our irrational number. So we got our rationals. Now we're going to talk about our irrational. Irrational numbers, if you think about them in their decimal form, they will neither repeat, so they're not going to repeat, and they're not going to terminate. So they're just going to keep on going in a crazy kind of way. So I can't really write out an irrational number here because I'd have to be writing forever and it would never repeat or terminate. I could write dot, 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 but you wouldn't really know what the dot, dot, dot means because we don't know where it's going. So sometimes we might use symbols like this. This is pi. We know that pi is approximately equal to 3.14, but the reality is it continues on and on forever without repetition. And in addition, we often think of irrational numbers when we talk about like square roots of numbers that don't resolve nicely. For instance, if I had like the square root of 25, that resolves nicely. Is this an irrational number? No. Clearly it's a whole number. It fits in the real rational side, right? So that's not what's happening here. Not just any square root or any radical, but a radical that does not resolve, where I'd have a decimal answer. This is going to also give me an irrational number. So if I were to turn it into a decimal, long story, very, very short, it would neither repeat nor would it terminate. It would not end. It would keep going on forever and ever, very similar to pi. And there's a few numbers that are going to be in that category. So now that we've explained these categories, we're going to actually get started on this example down here. Hold on. Okay, so here's the deal. We're going to use these letters, and they're associated with the letters that we used up here, to classify each category with which each of these numbers could belong to. So what I'm going to do first is I'm going to actually like look at the number and simplify what's going on. So here I've got the square root of 16, which I know to be 4, and 4 is totally in the rational kingdom. So I know that this number is real, it is rational, it's also a z, an integer, it's also a whole number, and it's also a natural number. It is not irrational. So I'm totally throwing that out, and I'm not going to put that down, so it's all of these. Over here with part B, I see I've got negative 185. Negative numbers do not fit in all the categories under the rational numbers, but it does fit in at least one. So it's real, and I guess I'm kind of being redundant by writing real since all the numbers we're going to talk about are real, but I'm going to put it down anyway. So real, this Q means rational, and yes, I could write negative 185 as a fraction, and it is an integer. It fits in my category of integers, but it is not whole. It is not a natural number, nor is it an irrational number. The square root of 20, I can simplify this, but I can't resolve it. Like, it's not going to come out to a nice whole number. And so because of that, it does not fit. It is a real number, but it does not fit in any of the other categories that we're talking about here. It is simply irrational. Over here, I've got negative 7 over 8. Negative 7 over 8 is real. It is rational, because remember, rational numbers are any numbers that I can write as a fraction, but it's not an integer because it's not a whole number, it's not whole, and it's not a natural number. Here we have this 0.45 repeating, right? That's what this means. And we talked about what that means. It means that this is not irrational, it is rational. Once I have a repeating decimal, I know that I can write it as a fraction, so it totally fits in the rational category. So I'm going to put an R here for it being real and a Q for it being rational. And we've done our first example. This next section is a bit involved, so I do want to talk about it in some detail. We have these concepts in mathematics that gives us the right to do things, okay? And so they're properties of certain things. So a property of addition is the commutative. When I think of the word commute, I think of traveling, like you commute to work or you commute to school or you commute to church or whatever. And so the commutative property says, of addition says, it doesn't matter the order. I can move these guys around, commute them around. I can move them around. Doesn't matter the order in which I add. A plus B is equal to B plus A all day, every day. Same thing with multiplication. A times B is equal to B times A. And this is significant because it's not true for subtraction or division, right? It does matter. Order totally matters when we subtract or add. The associative property says if I associate A and B first, meaning if I add A plus B first, then add C, it's going to be the same as if I added them in a different order, adding B plus C and then going back and adding A. And oftentimes the commutative property and the associative property are often confused, but what I want you to notice is that the associative property will often, not exclusively, but will often have parentheses to show an emphasis on doing one part of the operation before the other, but then everything else will be in the same order. Similarly, multiplication has the same associative property. If I multiply these two first, then this is the same as multiplying these two first and then coming back and multiplying the other term. When we talk about identity, I think about my identity as the person that I see in the morning when I look in the mirror. And so when I apply that mathematically, the identity property says when I add 0 to something, I'm going to get the same value back. So A plus 0 is A. Kind of like looking in the mirror, right? When I look in that mirror, I see myself. And it doesn't matter the order, right? We've given the right to write A plus 0 or 0 plus A. We know that the commutative property takes care of order, and therefore this is the identity. It's like looking in the mirror. Similarly, if I want to look in the mirror and I'm multiplying A times 1 is equal to A, I get the same thing back. 1 in the sense being the mirror, and 1 times A is equal to A. Inverse. Now this is kind of interesting and beautiful. The inverse in mathematics of addition is going, the inverse property is that if I add the opposite, I'm going to get 0. In a sense, we're kind of like evil twins. We cancel each other out. A plus a negative A is equal to 0, and negative A plus A is equal to 0. So once I add the additive inverses together, I'm going to get 0. And over here we have A times 1 over A is equal to 1, right? So if I multiply A by 1 over A, I'm going to get the number 1, or 1 over A times A, I'll get 1. So these are properties that you'll hear about in mathematics. Even in your college math class, you may or may not, but you'll probably hear about properties because it gives us the right to do things. It gives us in a sense, it's the basis with which a lot of the work that we do, particularly solving equations, boils down to using these properties. Finally, one that's really important is the distributive property. And I know you've heard about it, but I do think it's important to go through it again. What it says is if I have A times some quantity B plus C, I could literally rewrite that as A times one term in that quantity plus A times the other term, A times B plus A times C. And the distributive property doesn't just work if the value if the A value or the value we're multiplying is in the front, it also works if it's in the back again. So it's really me just multiplying each term inside of the parentheses by the number on the outside that's being multiplied by the whole sum. And so I could write it as BA times CA, or I could have written it as AB times AC. Both of those are the same. All right, so now we're going to talk about properties, and we're going to do some of these problems. And if I have to, we'll make a part 2 of this video. It's all to the good. So we're going to basically just name the property illustrated by each equation. So here I've got addition. So this is obviously a property over addition. And I see that I've got these parentheses, and that almost makes me think associative. But what I notice is that the same thing is being added in each pair of parentheses. So I'm not changing the association, but what I am doing is moving or changing the order, right? So what I would say is that this almost looks like associative, but this is the commutative property, right? This is the commutative property of addition. Property of addition. All right, there we go. Got it written down. And so we see that this thing, if you go back to the commutative property real quick, we see that A plus B and B plus A, and we've got this plus that and that plus this, and that's commutative. Here we've got obviously a property of multiplication, and we need to take a look. Well, what's going on with the parentheses? Here 4 and X are being associated, and here 3 and 4 are being associated. So we're changing the association. So this is the associative property, right, of multiplication. Property of multiplication. And that's all we're doing in that particular example. I think I'm not going to try to rush through the next couple of examples. We're going to call this part 1, and we'll look at part 2 in a moment. We'll start part 2 with example 3.